So the last section we're going through in Chapter 8 is another way to count things, which is combination. So in the last section we did permutations where the order mattered. So you had different levels of positions, you had different ways you were arranging them, and the specific order makes a difference. Now we're going to learn about the case when the order doesn't matter. So I'm just going to pick 3 people from a group of 10, and I'm not going to care who gets picked first versus who gets picked second. So that's called a combination. So a combination is a distinct group or set of objects without regard to their arrangement. So let's look at 2 different examples, and we're going to see which one's the permutation, which one's a combination. First one, you're going to adopt 2 puppies from a shelter that has 10 dogs. You're still making a selection, but it doesn't matter what order you adopt the puppies in. So in that case, this is a combination. However, if we're going to arrange 10 books on a shelf, that order does matter. So that would be a permutation. So that's the main difference between these 2. So let's try to look at an example and then see if we have a nice formula that results from this. 2 people are going to be selected from a club of 4 to form a committee. We want to see how many different ways can the committee be formed. So let's first start by labeling each of the members. Let's call them A, B, C, and D. And so we want to think of if we select our first member, we have 4 possibilities. We could pick member A, pick member B, C, or D. Then we're going to pick a second member. So from A, we have 3 options. We could pick member B, C, or D. Now here, when we get to member B, I'm not going to pick member A because this committee, it doesn't matter the order you get selected in. You're on the committee. If I put A here, this committee is exactly the same as this committee, and I don't want that to happen. I want unique ones. So if I pick B first, my only new possible committees are B and C get grouped together, or B and D. Likewise, if member C is picked first, my only new committee I could possibly have is with member D. So here you don't have A because AB is the same as BA. The selection doesn't matter. And then when we finally get to member D, I have no new committees I can form. I've accounted for them all. So in total, we have 1, 2, 3, 4, 5, 6 possible committees. So from a group of 4, when I select 2 of them, I have 6 possible options where the order doesn't matter. So what this is called is kind of choosing. From 4 members, I chose 2. So the number of combinations we're going to have is from n objects, we're going to choose r of them. So it's a slightly different formula. So the notation we have is NCR. So from n, we're choosing r. Likewise, we had NPR. From n, you're permuting r, where the order matters. One notation you can give for this instead is also these parentheses with the n up top to represent the objects you're picking from, and then the number on the bottom is the amount we're choosing. So this specific formula has us go n factorial. We still have the n minus r factorial, like we did in the permutations, but now we're also going to multiply by this r factorial. So it's basically kind of more selective than what the permutations is. Okay. So let's think of this last example. From 4 people, we picked 2. So the notation we had is from 4, we're choosing 2, which is the same as in these parentheses, from 4 we choose 2. So we have 4 factorial up top. Then from 4, we're selecting 2, and then 2 factorial is exactly this value of r. If you go to simplify this, the top is 4 factorial. 4 minus 2 is 2, so you have 2 factorial, 2 factorial. If you want to break this down by hand, 4 factorial is 4 times 3 times 2 times 1. Both of the 2 factorials are 2 times 1, so lots of stuff cancels, and you still end up really with just 6. So there are 6 ways to select the committee. Okay. So in a simpler example, when you don't have many objects, it's not a problem to go through and kind of draw these diagrams or figure out exactly the order of things in the permutation case. But the second you start throwing in more options, it would be way too tedious and kind of impossible to do it from hand. So let's look at the example. An ice cream parlor has 20 different flavors. You order a banana split and you're going to pick 3. We want to see how many different possible sundaes could I make. So pretty much from 20 flavors, I'm selecting 3. So from 20, I'm choosing 3. So with our formula, we get this factorial up top, then 20 minus the number we're choosing, which is 3, factorial on the bottom, and then multiplied by 3 factorial. So this is 20 factorial over 17 factorial times 3 factorial. At this point, you absolutely could plug it into a calculator. Really, you even have a button that will do exactly this. But you still want to be comfortable manipulating these. So if we go ahead and simplify this, 20 factorial, we can pull off the 20, you get 19 factorial, or you can keep going and get 18 factorial, or even go one more and get 17 factorial. And then in the bottom, we have 17 factorial and 3 factorial. The nice thing, 17 factorials cancel. So we get 20 times 19 times 18. In the bottom is 3 factorial, which is 3 times 2 times 1. So if we simplify a little bit more, 3 goes into 18 6 times. 2 goes into 20 10 times. This is 10 times 19 times 6. Or really, if the ice cream parlor has 20 different flavors, you could make 1,140 different possible banana splits. Okay? So this, you can see, it's going to be impossible for you to list every single outcome because there's a large amount of objects. Okay? So let's try another one. Matthew has 12 shirts and 6 pants in his closet. He must select 4 shirts and 3 pants to bring on his vacation. And we want to see how many different ways can he select this. So we have 2 events going on. We need to figure out how many different ways can he pick his shirts, and then how many different ways can we pick his pants. Then if we want the total possible ways we can do it, we just multiply those 2 different number of events together. So the first thing we need to do is figure out what are the number of ways he can select his shirt. So from 12 shirts, we have to select 4, which is exactly this 12 we're choosing are. So plugging into the formula, you get 12 factorial over 12 minus 4 factorial times 4 factorial, which simplifies to just 12 factorial, 8 factorial, 4 factorial. And again, if you plug this into your calculator, he has 495 different ways he could pick his shirt. Now for his pants, it's very similar. From 6, he's choosing 3. So 6 choose 3. Which, when we plug into the formula, gives us just 6 factorial over 3 factorial times 3 factorial. So he has 20 different ways he can select his pants. Okay? So there are 495 ways the first event occurs and 20 ways the second event occurs. So the counting principle tells us we just multiply those 2 together. So there are 495 times 20, or 9,900 ways he can select his clothes to bring on vacation. So he's got quite a few options. Right? All right, so now let's work with a catering service, which is something if any of you end up having a wedding, you might have to go through this option. So a catering service is making up trays of hors d'oeuvres, which are categorized as 3 things. You can have inexpensive, average price, and expensive. So you're forced to pick a certain amount of each category. You have to pick 3 of 8 inexpensive items. You must pick 5 of 9 average items, and then 2 of 4 options for expensive. So we want to see how many different ways can we go ahead and pick our choices for this particular event. So we've got 3 different things going on. The first thing is we have the average, we have the expensive, and we have the inexpensive. So if we go ahead and try and look at each of these, erase that back up. We want to count the number of ways we can pick inexpensive, average, and expensive. So we're told we have to choose 3 of 8 inexpensive. So that's exactly 8 choose 3. We have to pick 5 of 9 average. So there's 9 choose 5 ways to do this. And then we have to pick 2 of 4 expensive. So 4 choose 2 ways to pick the expensive one. So if you go through and calculate each of these, 8 choose 3 would be 56. So you have 56 ways to pick the inexpensive. You have 126 ways to pick the average and 6 ways to pick the expensive. So we just multiply these together since these are the amount for each event. And in total, you have 42,336 ways to select your menu. All right, so let's keep going. So you notice in all of these, the order doesn't matter. If you select this appetizer first versus this one, doesn't matter. So it's the key distinction between permutation and combination. So we're told Sue is having a dinner party. She has 10 different bottles of red wine, 8 different bottles of white wine. She's going to pick 4 bottles of red and 2 bottles of white to serve. And we want to see how many different options does she have to do that. So we've got red wine and we've got white wine. She's got 10 bottles and she's choosing 4 of them. So there's 10 choose 4 ways to do that. For the white wine, she has 8 and she's choosing 2. So in total, she has 210 ways to choose the red wine and 28 ways to choose the white. So if we multiply those 2 together, there's 5,880 different options. So that's how many ways she has to select the wine. Let's try another one. At a party, there are 75 people. Everybody shakes everybody else's hand once. And we want to know how many handshakes happen. Okay? So this one's a little different. It's not so obvious that it's going to be a combination. But basically, I'm going to come in contact with all 74 remaining people. If I pick the next person in line, they have 73 different people they could choose from. Really what we're doing is we need to count how many ways from this group of people I can pick 2 of them. And that'll be exactly how many handshakes are going to happen because the order doesn't matter. If I'm picked and you're picked, it doesn't matter who got picked first. We're going to just shake each other's hands. So I want to see from 75 people, how many different ways can I choose 2 of them? So if you plug that into our nice formula, you're going to see there's 2,775 ways to select 2 people. So that's exactly how many handshakes are going to occur. Right? So let's try one more that's going to make us calculate a probability. So there are 12 boys and 10 girls in a club. A committee of 3 people is going to be formed. We want to see what is the probability that the committee is all girls. So first thing I've got to do, we've got a couple different things. Remember, our probability is going to have the total number of ways in the bottom. So the first thing I have to do is figure out how many possible ways can I form a committee. So I have 12 boys and 10 girls, which means I have 22 people in the club. And I'm selecting 3 of them for a committee. So from 22 people, I'm picking 3 to form this club. So there's 1,540 ways to form the club. Now I want to see the events that are successful or the number of events that are successful for my specific outcome. So I want to see how many ways can we form an all-girl committee. There's 10 girls, I've got to pick 3 of them. So from 10, I'm choosing 3, which is 120. So the probability of an all-girls club is the number of ways to form the all-girl committee divided by the number of ways to just form a committee. So it's 120 out of the 1,540, which simplifies to 6/77, or about a 0.08. So if we were to select these people at random, there's about an 8% chance it would be an all-girls club, all-girls committee.